can
This
use later.
conference will now be recorded.
So I'm going to start with, I sent you a Word document that describes what I'm going to walk through today. I'm going to put this on the screen, make it a little bigger because we're going to come back to this at several times. So the intent today will be to walk you through two different tools. One is an online user interface tool, and this is the website right here. That is a dedicated Amazon Web Service website that is for Sierra Leone, only for Sierra Leone, and it allows you to look at these online tools and run the data cube. So this is a free and open access for you and other users around your country to use this. I'm going to demonstrate for you a water extent analysis. I'm going to show you, and there's some examples here in this document, of water detection and what it means. I'm going to show you this in a moment. Here's an example output. I found your region to be really interesting near the coastline. I think I heard someone say they were from Maritime in your audience, and some of the information that we can get out of this tool is quite remarkable because you have a very complex area of wetlands around Freetown and in the coastal region, and you're going to see some of the information is really quite interesting. So I'm going to show you how to do all these things and how to look at an individual pixel, and then after that we're going to jump back to the Jupyter Notebook. So that's just an intro of where we're headed. So when you go to your user interface tool, this is what it's going to look like. I'm at a slightly different address here, so don't worry, it works exactly the same for you. This is just a different address. But I first would go to tools, and in here you can do mosaics, you can look at cloud coverage, you can do urbanization, fractional cover, NDVI. There's a number of things you can do, but they're going to work very similar to this demonstration I'm going to give you for water. So what I'm going to do is go into water detection, and when you come in here, you are going to choose your Sierra Leone. And this now shows you the bounding box for the extents of your data cube. So the bounding box is a little larger because some of these scenes, poke out a little deeper in all directions, but basically your entire country is covered. So what this means is that you have, in this case for Landsat, you've got 17 years worth of Landsat data for Sierra Leone and allows you to run these analyses. So I'm going to zoom in on an area of Freetown and show you an example. I did one, the plot that you see in the report is right over here on the eastern side of Freetown. I'm going to show you this other interesting spot. It's an island over here, Cogbelly Island. And the first thing we do is we click on the corner and we drag a box, and that creates an analysis region for our case study. I can do a start date and an end date. In this case for the water, you can go all 17 years. It runs pretty quickly. So I'm just going to let this run. So what this is doing now, and you can see it running in the bottom, this is taking all 17 years of data, and it is searching through and deciding how often every pixel experienced water in those 17 years. Now, if a pixel is blue, dark blue, that means it experienced water 100% of the time. And here's what it looks like over here. This is the legend. So on the right-hand side of the screen, I clicked on the legend. So here's what we get for this island. Very interesting. Everything in blue is 100% water. That means the water was there every single time step that we saw. But if you look at this island, it's quite interesting. I would have expected, if this island is just a typical island, maybe it has a jagged coastline and some altitude to it, some elevation, this would never experience water. But in this case, this island has a lot of wetlands and obviously has a lot of water at times of the year, at times in the history. So if you look here, things that are red are areas that only experience water 0 to 5% of the time. So this particular area here, we can click and find out when it experienced water. But what you're going to see is that this could have been just 1 or 2 times in 17 years. This area here is an area that looks like it probably experiences seasonal flooding, probably during a rainy season, or it might have experienced some flooding that persisted for a few years, because it's somewhere between yellow is 5 to 20%, like this spot, and this green spot here is about 20 to 30%. So let's click on this yellow spot in the middle. So there's this little eyedropper on the left-hand side. So first I'm going to get rid of that. This eyedropper on the left-hand side allows you to pick one pixel and do an analysis. So when I click it on the green spot there, it tells you, whoop, I had a little problem there. I don't know why it not working here. There it is. All right, it's plotting, it's generating the plots. So I'm going to do it for the red spot. It didn't like that green spot. It had an alert. So what this is doing now, and we'll give it a moment, it is analyzing the pixel that I clicked on. And by the way, you can see the lat long positions up in the right-hand corner as I move around. It's taking this particular spot right here, and it is going to generate a time series plot of the clouds that it experienced, as well as the water that it experienced over time. So let's let that give a moment. We're going to go back, and I'm going to show you in the report what it's going to look like. Whoop, when it's done. Hang on, that was a wrong document. That's your document. And so it's going to look like the font. Oh, it just came up. So I'm going to go back now. Here it is. So on the right-hand side of the screen, might be a little difficult for you to see. That little spot there experienced water 2 times. There it is, 2 pixels. Two periods in time. And if I fall down here and look on the time scale, it looks like about 2005, and then maybe again in 2006. So that spot there only experienced water 2 times in 17 years. The rest of the time it was non-water, which is 0, and water is 1. But if you look down here, you've got a lot of clouds. A clear 1.0 means clear scene, 0 is cloudy scenes. You have about 50% clear, 50% cloudy. So there's a lot of clouds in many of these areas. Let me click one other spot. I'm going to start a new one here. And let me click this little spot, see if we can get one of these green areas to show up. There we go. So this is the green area, which looks like water might be coming in through this path along here. But it's curious why that is green, because that's 20% of the time. And we'll give that a moment to generate the plot. In the meantime, I'm going to go back over and show you the plots that I ran in the report. I ran this in this report. This is just off of the coast of Freetown, I think right across on the east side. And you can see here how many times it experienced water in that green. This is probably seasonal flooding. So it could be every spring or summer. I'm getting seasonal flooding. I had a little drought period here in about 2008 or 9, and then again, seasonal water. And then you can look at another non-water, and this is the red one. So let me go back to the spot that I just ran. This area right here in green when I clicked on it. And again, if you want to know exactly where this spot is, zoom way in and move your cursor around. You see the lat long positions? It'll tell you exactly where you're positioned when you drop the marker. That's the exact lat long in the top. So if you look at this spot that we just picked, it experienced water many times in 17 years. And what you see, again, I would suspect this is probably a seasonal flooding instance, because it looks like it occurs just about every year with some gaps in between where there's non-water in between. So it's probably rainy season, dry season, rainy season, dry season. That's my guess, with a little bit of a drought period here, maybe in the 2008 or 9, where you did not have significant rains. So there's some really powerful stuff here. For those of you that are interested in coastline dynamics, there's a lot that can be done looking at the timing. And if you were to look inland, here's another thing that's powerful to do. You could look inland at some flooding and look at water regions. So if I'm looking at this area here, Port Loco, so let me just run a quick case here. This is a city nearby, and I'm interested in just what's happening along this river here in Port Loco. I'm going to run a case here. We'll let this run just for a moment, and then we'll come back to that. But This one looks like it's going to run quite rapidly, so let's just let it continue. These, as long as you choose a reasonably small region, don't pick the whole country, these things run pretty rapidly. And as you can see, this is doing 17 years of data for this area. It's really quite remarkable. So there it is. What's interesting about this is that I would have expected that river that flows along here to be water all of the time, but it's not. So what's interesting is that either this is very cloudy and maybe there's a lack of data, so we can go back and look at that. But what happens is the river here is blue, so here it is in existence permanently. But once it gets to this point, this part of the river here doesn't really exist hardly at all over 17 years, just some very sparse water. So this tells me that this river system here, the Bankasaka River, it does not show water very frequently in and around this area. So in here, yes, probably because it's wetlands, but not here at all or in very rare times. So again, we can use this information in time, and it's quite impressive what we're able to do. So I'm going to close that out. For now, I'm just going to delete these cases that I ran, and so that we can move on to a few other instances. So I would, wrong document again. I want to come back now and show you what I think is the most exciting part of the DataCube toolset are these things called Jupyter Notebooks. Now, a Jupyter Notebook is a user interface that allows us to run Python scripts that basically do everything that is in this user interface tool. So all these algorithms are available with Python scripts, but there are some powerful algorithms that we don't have in the user interface tool that you're going to find run beautifully and produce some incredible results with just the code itself in Python. So when you go to your address here, the Jupyter Notebooks, if I go to this website and use this password, and by the way, I'm giving all this website and password to you. If you would like to control this a bit on your end, we can change this password to anything you like, and then you can give it out to others as you see fit. Just because by me putting this here in a document and you spreading the document around, a lot of people could have access. So you have to be quite careful because people can change the files on here quite a bit. So anyhow, here's how you get to your Sierra Leone Jupyter Notebooks. And when you go there, I have put all of these file names that are referenced in this document, I put them there for you. So you can run exactly what I ran today. So I'd suggest a few things that you try to do. When you go there, it's going to look like this. And you're going to see a list of Jupyter Notebooks in there. Matter of fact, I'll go to your site now just to show you what it looks like. And here's your site. You don't have too many Jupyter Notebooks, but here they are. All of your training notebooks from Africa are there. There's some notebooks that show you how to export GeoTIFFs and export NetCDFs. But these 4 notebooks at the top are the ones I'm covering today in the training. If you want to run them, what I would suggest is to leave these notebooks alone and don't modify these, but copy them. And the way you copy them is I click on it and I just do File, Make a Copy. And what it does is it increments the name copy 1. And let's just say I click on the name and on the end I put Brian and I hit Rename. So let me show you if I go back to where we were. Let me see. Here's your home. I've now created Demo Cloud Statistics Brian. So the Demo Cloud Statistics still exists, and Brian is the new one. And I can delete it just by clicking there. I'm going to shut it down first, and I'll show you how to shut down things, and I'll just delete that. So there I have everything that I want. Clouds, all the things I'm covering today. If a notebook is open and it is running, you go to the running tab and you can see what's open. So someone was running some demos over here. I'm going to shut those down. I don't think those were running, but Demo cloud statistics. Since I clicked on it, it's open and it's taking some memory. So when you're running analyses, you're going to look here and see in the running tab what's running. This is how you keep a pulse on who is using your resources and what files are running. Because if you get a lot of people running jobs, you're going to want to shut some of them down by clicking shut down. That's what you would like to do. So I'm going to go back to my screen, and you're going to see that I have about 5 different notebooks running because I'm analyzing some of these for you today. But I'm going to start off with this one on cloud statistics. So the cloud statistics is a great way for you to look at the scenes that are in your data cube, the time slices, and determine the cloudiness. Here's what I found for Sierra Leone. You have a very cloudy region, extremely cloudy. So what this allows you to do, and I'll run a sample case, it's going to give you a table of the dates and the cloud percentage. It's also going to give you a plot. So look at this plot. This plot here is over Freetown. I took a region over Freetown and I plotted all of the years from 2000 through 2017. And this is the cloudiness of your time slices. So there's a couple things here you see that are quite interesting. The first thing is, if you had a really clear area with not a lot of clouds, all your scenes would be up here around 1.0. With 1.0 means this is clearness, and 0 is cloudy. But you have a lot of cloudy scenes. You have a lot of scenes down here that are cloudy or maybe 20% clear, and then you have fewer up in here. Now, another thing happens is when you had clear scenes up until 2003, they were always 1.0. There was a problem that occurred with Landsat in 2003, and some people call it the banding issue. Other people, it's called the scanline corrector. There was a problem with the instrument in 2003, and what happened is the most you will see in terms of clean pixels is about 90% after 2003. That's because of this scanline error. So the reason you see a drop from 100% clean for some scenes to about 90% clean is this scanline error. I'll show you what that looks like in a moment. So let's go back to, this is what it looks like. I'm going to walk you through not the details of the code, but just I want you to see the different blocks of the code, how you modify things and how you run things, because this is what you're going to want to do when you modify this code and use it for yourself. So if I'm running this cloud statistics, the first thing I want to do is I want to browse what's in this this script. So there's a few things in the script. Many of these you will not modify. Matter of fact, the majority of these you will not modify. This thing loads the data cube configuration. This one lists the products. So you actually have access to other cubes besides Sierra Leone. So there's more here, Ghana, Kenya, but you only want Sierra Leone. There's your Landsat 8 product. So you can also look at Landsat 8. So this particular thing says, I'm going to load this product and this platform. I'm going to load the Sierra Leone cube and the Landsat 7. So this is where you might change the product or platform if you desire. The next thing it does, it says, I want to print the extents of the cube. This shows me that this cube goes from January 2000 through January 2018. This is the latitude boundary, and this is the longitude boundary of your cube. So you've got a pretty big cube. It covers your entire region. I then came down here and I was running several cases. So I ran a case last week. I was training Tanzania. So this is a Tanzania area. But for you, I'm looking at a forested region west of Freetown. And I pick a lat-lon bounding box. So when you run analyses, you don't want to run analyses for the whole country because it'll be really slow. You want to run them in blocks. Just test them out, see how fast they run, and then enlarge your block if you want to do larger lat-lon boxes. So I'm running an area over Freetown, 2017 to 2018. So basically the year of 2017. So here I'm going to change this information if I'm going to run something new. This you will not change. This is all just basically sifting through and unpacking the data and cleaning up the clouds. And then finally, this is the report. So for this case I ran in 2017, it basically says I had a time slice January of 16th, February 1st, February 17th, March 3rd. Notice the cleanness, 91%, 91%. That's, remember, because of the scan line error, that's actually 100% clean. This is a very cloudy scene. This is completely cloudy, 0, and I'll show you what it looks like. That one's pretty cloudy, and you can see there is not a lot in 1 year. You've got a few in January and February. You have a decent scene in May and a decent one in December, but in between, not so many. If you see this number out on the side, 0 through 16, we use that number if we want to look at individual scenes. I'll show you this in a minute. Here's what the plot looks like. So this is a plot of the cloudiness from this table in a plot. So you can get an idea. A couple good scenes here, one good scene at the end, a lot of clouds in the middle. This is very typical of your area. And look what this looks like. Here is the scan line error. So unfortunately, these little ugly lines are an instrument artifact. Here's your clouds right here in the corner. This was index number 7. I can change this here. If I want to go up to this table, I was just plotting that scene. Let's say I want to plot this scene right here, index number 5, 46% cloudy. I come down here, I put in index 5, I just modify that, I hit shift return, and when you do shift return, it runs a single block. I will tell you in the notebook training that we had in Kenya, in Nairobi, there was a segment in that training manual that teaches you how to use these Jupyter notebooks, how to run them from top to bottom, and how to edit cells. I'm just doing it pretty rapidly here today, but this little trick about, I modify this to 6 and I hit shift enter, you can't see me doing that, but it's running one block. So notice how cloudy that scene was. Let's go back to number 5. This scene number 5 right here. If I go back up to the chart, it's 46% clean, so it's 54% cloudy, and if you look at it, it's pretty bad. Lots of clouds here, a little bit of land, some good pixels here, but quite a few clouds. So this is a good way, this notebook is a good way for you to look at individual scenes, time slices right here, and cloud cover for a number of scenes. So I urge you to take a look at this one. It's really nice to look at, and I can change this and run individual years. I'm not going to do that now because I'm going to jump over to the more interesting notebooks. So the next thing I want to do, in the meantime, as I'm going through this, if you have questions, just kind of jot them down, and at the end of this training, I'm going to leave some time to come back and answer your questions. For those of you on the other line, if you could mute a few people, perfect, thank you so much. There's just some good background noise. The next thing I want to show you is...
Hi, Brian.
Yes.
Sorry. Hi, Brian. Please, can you, I'm not able to reach the guys in Senegal. I can see that they are the ones talking and the noise from their end is actually distorting the whole thing. Yeah, so okay. I'll send messages to them by SMS to mute their end. Thank you.
Okay, sure. So I'll just continue, correct? Okay, I'll continue. The next thing I'd like to talk about is the study of urbanization. In some of my interactions with Victor, he was telling me about some of the use cases that were of high interest to you. The next 2 notebooks we built and modified specifically for you, Sierra Leone, because I think you're going to find these to be quite powerful and interesting. They're going to allow you to look at urbanization and land change. So this first one, urbanization. There's a number of ways we can look at urbanized areas. So I'm first going to show you the outputs here, and then we're going to go to the Jupyter Notebook and show you how it runs and how it works. So here are some example notebooks, or some example outputs. On the left-hand side, I'm going to make this a little bigger here. Let me see if I can do this. On the left-hand side is an image. This is a Landsat 7 image where I enhanced the colors. I took it into Photoshop just to brighten it up. And this is Freetown. So obviously, areas that are urbanized are going to look lighter in color in a visual image. This is just a normal RGB. This would be what it looks like to the human eye from space. Lots of urbanization along your coast, and then you have a forested region here, dense vegetation in the central areas. So let's look at this in another product, and this product over here is called fractional cover. And what this product is trying to do is it's trying to look at the pixels and iterate the portion of the pixel that is green vegetation, non-photosynthetic vegetation, which is blue, and then areas which are bare soil. And this is also another indication of urbanization because the green areas pop out very brightly. You pretty much have to disregard water because it gets confused when it sees water pixels. And here, areas here are either like appear to be like a bare soil when you get really close to the surface because these are probably sandy beaches and these are probably wetlands. But then areas here like urbanization tend to show up as blue. So this is just another way to look at the data. So the ones that are more powerful, I'm going to show you here. So what I have done in this notebook is I've taken probably the most popular spectral index that we use for urbanization, and it's called a normalized difference buildup index, NDBI. NDBI is quite useful. It allows us to look at the ratio of two bands in Landsat to distinguish urbanized areas. And what I'd like you to do is if you look at what I have on the screen here, on the left-hand side is a website called the Urban TEP, which is a thematic exploration platform. This was built by the European Space Agency. And so what I did was I wanted to see how good is the data from the data cube compared to what other people are putting out there. On the left-hand side is the urbanization of Freetown in 2012, according to this website. The data in this website on the left-hand side, this data here, was built up from radar imagery for 2012 from radar taken by TerraSAR-X and Tandem-X, which, by the way, is very expensive data. It's not free and open. So the bottom line is, can you reproduce what they're doing with this expensive data in a data cube using open data, which my result is on the right-hand side? I would say if you compare these two, they're extremely close, and many of the features look very similar. We're actually getting a bit more urbanization in this result, but I would say that it's very good. And if I compare that and I say, okay, this is urbanized area in 2012, and I compare it to other years, the power of the data cube is I can track your urbanization year to year to year, whereas this product here is only one single point in time. And I have no idea when they're going to recreate the next point in time, but this is 2012. So here's what I get. I think and what you do is you take this index and you threshold it, and I say, show me all of the pixels between 0 and 0.3, and there is the answer. So if I look at this, I might count the urbanization in this scene, and I might say, of all the pixels in this scene, including the water, but it doesn't matter because I just want to compare the number of pixels that are urbanized from one year to another. 14% of the pixels in this scene meet the threshold, and therefore they're red. So let's look at prior years and see how this has changed. So if I use this same exact approach, look at the difference here between 2000 and 2017. This is 17 years of urbanization in the Freetown area using the exact same algorithm. So in 2000, on the left-hand side, 7% of the pixels were urbanized. So again, don't forget, you've got a lot of areas that are unurbanized here, which are inside, and you got water. But if I just compare the increase in urbanization, 7% here, 18% here, I basically could say the difference between these two is about 11%. So you've had, in terms of urbanized area, an 11% growth in urbanized area just using this, this product here. So 17 years, 11% change in urbanized area. It gives you a decent idea of tracking urbanization. So if I look at the detail of this, notice this area right here, inland. That area right here is all completely new. So this is an urbanized area, and I'm going to show you there was some deforestation that occurred to make that urbanized. Notice just inland of the coast, a lot of urbanization just inland around the coast, and a lot more urbanization here on your eastern eastern border here. I think the water comes in here and there's eastern border. So it's interesting to see the pockets or the areas where the urbanization has increased. Now, go back again and look at 2012. So you see in 2012, this area here was just starting to grow, but look how dense, it's denser by 2017. The area along the coast here was not that dense in 2012, much more dense here in 2017. So just in 5 years between this part and this part, quite a bit of growth here. So this is very powerful. So let me go back and I'm going to show you how to run this. We're going to come over to the urbanization area here. And the notebook that I ran here, I'm going to walk you through it top to bottom. And I'm going to show you where I have changed this notebook to run for a different part of Sierra Leone, just to show you you can do this anywhere in your country on any city. Again, this notebook works like cloud statistics. I load up some things and I import the data cube and I import some plotting functions. None of this changes. I choose the Landsat 7 Sierra Leone cube and I print out the boundaries. That's fine. I just want to make sure I've got the right cube. I show the boundaries on the screen. I've got the right cube. The next part is I've got to pick a region. When you work in notebooks, the way you change things, if I put a hashtag in front of a line, it's a comment line. So I have commented out the Freetown region, which is everything you saw back in the data cube training. So when I was running, this area here, this was the Freetown analysis. That was the area here. What I did this morning before this telecon was I went to your second largest city of Kenema, and I said, well, let me do an analysis over Kenema and take a look at it. So I chose latitude, longitude, extents. I just went into the map and I clicked. I like to use this map here. So if I click on this map and I want to do this city up here, Kabbalah, I zoom in on Kabbalah, I click in the bottom left corner and I tap my button and I see the lat lon, and then I click up here and I pick another lat lon. I jot those down on my piece of paper, and that's what I enter here to create a new region. I create this region and then I plot it out. Oh, and I pick a time set and I say, I'm just going to look at 2012, January 2012 to January 2013. So I'm going to look at 1 year. So here it is. I plotted out. There's Kenema. So this is the area that is around Kenema that I'm going to look at. So let's do an analysis here for 2012. I ran the analysis and I've got 22 time steps. So I've got 22 scenes. That's great. A decent amount of data. I create a median mosaic. This is what it looks like. This is just plotting out some intermediate products. This is the RGB. Notice the RGB. This is the visual. Notice the streaks that are through here. This is this Landsat 7 banding problem, but it's pretty clear. Not a lot of clouds. There's just a little bit of streakiness because it's trying to fill in the data when it can to fill in those streaks. So the data for this part is slightly different than the data for this part because it's a different time step. That's why you get something that appears different shading. This is the fractional cover. There it is. Remember I said a lot of this urban area is either red or blue. It's looking pretty good. So let's look at what this is doing. This is defining a variable. This is defining NDVI. It says NDVI is near infrared minus red divided by near infrared plus red. NDVI, this is the big thing that you will use. The normalized difference buildup index is the SWIR band minus the near infrared band divided by SWIR plus near. That is just, somebody has figured out that the combinations of these bands does a nice job with urbanization. So let's plot some of these things. So the logic here says I'm going to plot SWIR versus, this is NDVI plot from 0 to 0.2. It's a little sketchy here, but if I change the Vmax to 0.3 and replot it, I can see a bit more data. So most of this, there's not a lot of heavy urbanization. So I go to 0.1, I can darken it up. It looks like that. So you can change the boundaries of the scale. That's what I'm doing there, is just changing the scale. There's vegetation index. You would expect vegetation around the city, a lack of vegetation in the city. That makes sense. This is another index called buildup index. So let's look at threshold. This is a threshold logic that says the way I create these threshold plots that look like this, I am going to say I want to create a minimum threshold of 0, a maximum threshold of 0.3, and I'd like this plot to be a threshold plot of the NDVI index from 0 to 0.3, and I want to put it right here on the screen. And then at the end, I want to count up the pixels. This is counts, and it says there are 7.47% pixels inside the threshold. So that's how I got the numbers in this area here. So when I say 7.3% urban area in 2000 right here, I got that by looking at the values that were printed out at the end. Now, this is 2012. So I thought, well, wouldn't it be interesting to go compare this to that ESA product that we looked at? So I've opened up another tab here, and here's the ESA product. This is the built up in 2012 over the city of Kenema according to that European Space Agency. So look at this, and I'm going to jump between the two, and there's this one and this one, and they're quite similar. So you'll see this little patch up here. What our results show is a little bit more urbanization here. You see how they're connected? There's that patch, and they're a little bit connected. So it's showing in our analysis more urbanization here. You can see some of the lands and the lines and the banding through here. It's not great. But let me rerun this real quick just to show you. I'm going to run it for some of the nearer years like 2017 and 18. So I'll come back to the top and I'll say, let me just rerun it for 2016 all the way to 2018. So in case I have a lot of clouds, this is 2 years worth of data, mosaic together to give me one answer. And the way you run the whole thing again is I do kernel, restart run all, and now I'm running this entire notebook from top to bottom. When it runs a notebook, you see the blocks have a little star. You see these little stars. That means that it's running. If you're impatient like me, I just scroll to the top and I watch it run. And every time it runs a block, it starts to sequentially number the blocks. So it's gone through, it's now run this one, it's run this one. Notice where it's stalled. It's stalled on loading the data. That makes sense, because that's a slow step. It's going into the data cube right now. It's pulling out all of the data from these 2 years, and it's pulling out the data, only the data that I want over the city of Kenema. So before it does the analysis, it loads the data into memory. So it's done. It loaded the data in the memory. 76 time slices. Latitude, there's 408 pixels in latitude, 334 pixels in longitude, and 76 time slices. So this is important to look at. Now let's go down. It should have run the whole thing. It's going to run the whole thing. There's a nice mosaic. It looks pretty clean. And I run to the end, and let's look at what we get, and there it is. There is the urbanization extent for Kenema from 2016 to 2018. So that's in the last couple years, and I compare that to 2012. So again, 2012, most of it's centralized here, and look at the difference in 2015, 16 to 18. There's more urbanization out here and a little denser in the center. So again, if I go down and look at the percentage, 11.97%. And if you recall, I think the number was like 7.9% in 2012. So if I just compare 2012 to this result, I'm looking at about a 4% increase in the urbanized area just using this algorithm. So you can run this anywhere in your country, look at this urbanization extent. You might want to play around with the thresholds a little bit to try and get some accuracy here, because as you change the threshold, it picks up more noise. But this is a pretty good way to look at urbanization. I think it's a very good way. So I'm going to go back now. The last thing I want to show you, and it gets even more exciting, and this is land change. I have found this to be one of the more interesting notebooks in that if I want to know what's happening to the land, I need to know when it's changing. And one of the things that happens the most, especially in urbanization, is, I saw this around Freetown. You went from an area that was forested to an area that became urbanized. And what happens is over time, you just slowly eke into the forested areas. So what we know when it comes to land change, we look at this index called vegetation index. For those of you that are familiar, NDVI is the most common vegetation index. We know that forests have an NDVI value of 0.6 to 0.9. It's pretty typical. They're dense vegetation. They don't change a whole lot, and they're very dark when you look at them from space. So typical for forests, 0.6 to 0.9. So what I do is if I look at an area that had an NDVI of 0.6 to 0.9, and then I notice that that NDVI has dropped significantly as in later time periods, I can then pull that out and I say that is change and probably deforestation. So I ran a case over Freetown near your urbanized area. So this is your urban area. This is a forested area, and this is a forested area. And you will notice how this area has changed as your urbanization increased here and here. So let's look at what happened. This is a scene in 2001. Lots of vegetation up to the north and the south, very little urbanization right here. This same scene in 2017, a lot more urbanization. We saw this in the last notebook where the urbanization increased quite substantially. And what I get here is deforestation occurred all around here, a lot of deforestation here and deforestation here to create this urbanized area. So what does this look like in the data? A couple different ways we look at it. The first thing we do is I want you to look at the image on the left. The image on the left says all I wanted to do was I wanted to show every pixel that had an NDVI of 0.6 to 0.9 in my baseline year of 2001. This basically said all of these pixels here were forest in 2001. I ran my analysis for NDVI anomaly, and for each of these pixels, what I said was I want to go look at 2001 to 2017. I want to compare the pixels in 2017 with the pixels in 2001, only the forest pixels, that's all I care about. I'll mask out the rest of them because they're masked out. So right here, these are non-forest, so I mask them out and they're black. So if I look at just the forests, this is the NDVI change. And look what has happened. Anything in red has had a substantial loss in vegetation. So the NDVI has dropped dramatically. All this area was devegetated. Why was this devegetated? Because this area was urbanized. Devegetation occurred, the urbanization grew, and it mostly occurred right on this area. There's some devegetation along this perimeter. There's a little bit of green here, but it's very slight. It's like 0.1. So there's an increase in greenness here, and it just may be because 2017 might be a little wetter than 2001. So this area here may be a little moister, so it's showing up a little greener and a little greener. But I'd only be looking at major changes, and this is definitely a major change. If this was dark green, then I would say, oh, that vegetation could substantially changed. But this is dark red, huge loss there in forests. So the last thing is, how can I count up these pixels? And I mask them. So the last thing we do is we say, I create this threshold image right here. This is where it gets, I can get at the change. I say, if I go back to this image here, and I'm going to count all of the pixels that are between 0.2 and 0.6 loss, which are the ones in red, and I'm going to threshold them, and this is the image I get here. So every pixel that had a loss in vegetation between 0.2 and 0.6 NDVI, and that was within the forest mask, which is the area in the middle, I colored it in red, and this is what I get. So this clearly shows the area that lost vegetation or was deforested. All of this area was deforested over 7 years or 17 years, and same with this area down here. Very interesting. So you can do this at any spot in your country and run this vegetation change. What was interesting is I looked at the decrease just in this area here. If I count those pixels, 18% of the region experienced devegetation. It was pretty interesting. And if I say, well, if every pixel is 30 meters square, which is about right, it's pretty close to that, you had 14.5 kilometers square of forest loss in this area right here in 17 years. So let me go back again and just show you quickly how this runs. So I'll leave some time for questions. I want to show you how this runs in the notebook. There it is right here. I'm going to go top to bottom and show you the products so that you can see how this comes out. But if I, well, sorry, I'm flying through this so quickly. I'll go back to the top. Loads up the data cube. Now, what's interesting about this notebook, it's using both Landsat 7 and Landsat 8, which is great because I just get more data. Landsat 7, Landsat 8, I'm going to load them in. I take that back. This particular one's only using Landsat 7. I just noticed that the product wasn't turned on for 8. Again, I chose a region west of Freetown. There it is. And I go down and I run through and I am doing a max NDVI mosaic. This is what I chose to do. Here's where I change my baseline and analysis time period. This says I start in 2001 to 2002. So my baseline time period is January 2001 to January 2002. So basically the year 2001 is my baseline. I want to compare that to the year 2017, which is my analysis time period. I put a threshold range of 0.6 to 0.9, which basically says I only care about forests. And then I run this analysis. I get a mosaic at the baseline, a mosaic at the ending. There's my forest map that says this is only the pixels in the forest area. And again, there's the anomaly product and so forth to the end. So these were all the things you had. So let me just run one for you real quick where I'm going to change the area and show you how to rerun this. So let's say I want to pick a different spot. First thing I'm going to do is I'm going to zoom out. I'm going to pick a different area. So let's say I want to look at this area near Waterloo. And I want to look at devegetation and urbanization around Waterloo. So I'm going to look at, I'm going to pick 2 corners. I've got to pick a corner. So I'm going to start in this lower left corner. I'm going to jot this down, 8.2876 minus 13.083. Pick a corner up here in the top right. Let's go, we're going to look at right there, 8.346 and minus 13.0157. So I've jotted these down. I'm now going to come up here. I'm going to create a new one. I'm going to call this Waterloo. You can watch how I do this. This is the Waterloo area. And I'm going to create a new lat line. I'm just going to copy this down for now. And I'm going to change it. I'm going to comment out the old one. So now I'm running this new Waterloo region. I'm going to change the lat long boundary, 8.2876346, and I'm going to change this to 083 and 0157. Now, if I do this and I just hit shift return, there it is. That's what I'm analyzing. So the analysis is going to show possibly some devegetation along here as this area of Waterloo expanded, and I can see it's an urban area. So let's see in 17 years how much devegetation occurred. And by the way, I have never run this analysis, so I'm going to run it right now on the fly. I'm going to restart run all. We're going to run this whole thing, and we're going to look at what has happened to this area around Waterloo. So this one will take just a minute or two to run, but this will be the end of our analysis, or the end of our training here, and then we'll open for questions. So again, I'm going to come to the top and watch this run. It's loading pretty quickly. Right now it's stuck on this, loading the analysis. All right, boy, that ran fast. I'm happy to see that. It's creating a baseline. There's the mosaic. That's the baseline mosaic. It's a little bit dirty in here. So again, there's some areas in here that aren't so clean, but a lot of vegetation. And then later on, more urbanization. So these are not the best mosaics because there's some problems in here with clouds. So what that means is that I might want to take the time scale. Instead of 2001 to 22, maybe I'll make that 2 years long and make that 2 years long. That'll give me more clean data. But let's see what it is anyway. There's the threshold. So this basically says these green pixels were forests in the beginning. Now, these could have been urbanized areas or these could be clouds, but if my median mosaic was clean, these are the forested areas. Notice, and white is non-forest. So there's like a little river running through here. That's non-forest, obviously. So these are the forested areas, dark green. There's the anomaly. Pretty interesting stuff. All of this area here was devegetated pretty severely. Everything in red, and this is the area around Waterloo. So my guess is this area here in dark was the urban area in the baseline time period, and all of this was devegetated over time. And you have some slight increase in vegetation here, but it still stays. So again, if I use the same threshold I used for the last analysis, I'm just going to go down past this. There's a few other intermediate products. There's the area there that has been devegetated. Everything in red is an area that was highly devegetated, a severe loss in NDVI. So my guess is that was definitely deforestation, probably back here as well. And if I count that up, we lost 30% of the area around that Waterloo just in this analysis here, significantly change in vegetation. Now, is this answer correct? May or may not be. That scene looked a little dirty to me in terms of clouds. I would probably run this because I'm not happy with some of these areas here with the cloudiness. I might run the baseline for maybe a 2-year time period, maybe even 3 years to make this a cleaner scene, and run the analysis for maybe a 2-year time period, and maybe it'll clean it up a bit. But the bottom line here is that this area around Waterloo, this area here, I think there was a lot more. This is a more recent image, but this area here had a lot of vegetation and a lot of vegetation here, and this urbanized area here has grown significantly in 17 years. So I'm going to stop at that point and entertain your questions and say thanks for listening, being attentive there, and let's see if this works. Thanks for your time, and if you have any questions, now would be a good time for me to answer those.
Yes. Yeah, I must say the training on data cube has been remarkable. I'm also happy that we can use the notebooks to modify the algorithms so that we can get a customized result. But I want to suggest something. I want to suggest that we have a brief interpretation of the legends or the resultant images so that somebody who is not an IT person or maybe is not literate in terms of data cube would be able to interpret some of those pictures to know exactly what they are talking about. And also, I want to know what determines the choice of latitude or longitude. For example, you want to look at the urbanization pattern of Cambia. How do you determine the latitude and the longitude in order for you to be able to get the resultant images?
So let me, I think there were two things in there. I didn't understand it all, but let me try to repeat, see if I have it correct. You were asking about interpretation of the data and the importance of interpreting some of these results.
Exactly.
Okay, and that is very important. There is no doubt, now I'm going to turn this off temporarily. There is no doubt that when I look at a result like this for the area of Waterloo, you know, you don't want to go make decisions on that and say, oh my gosh, there's, you know, 18% loss in vegetation. This is a horrible area. We need to change something drastically. What you want to do is you probably want to run this analysis. You want to compare it to some known maps. You want to interpret this data and get an idea, is this telling you the correct story? And do you have some information to justify this result? Because with these analyses, you can generate all kinds of products, but you have to be careful and you have to validate them and understand them and feel comfortable that it's telling you the proper story. And so I urge everyone, this is just an analysis using satellite data from space, but you have to think about what it's telling you. But there's some powerful information here. I mean, let's face it, vegetation from space is pretty easy to see. And if the vegetation is lost, that's also pretty easy to see. So I would definitely say in this area, there's devegetation occurring. Is the extent of it 18%? I'm not sure. That's what you'd need to validate. So I think the second part of your question was, I think you were asking, how do you pick a different lat-long position? Is that what you were saying? If I were to look at all of Sierra Leone, I can go in and zoom in any part of this, and the way I pick my lat-long position, I just use this map in the notebook. You can do this elsewhere, right? You can do this in a Google map. So if I want to do, like I did earlier this morning, I want to do this, let's say, city of Bo. What I do is I just click around this map, and if I click bottom left corner, up pops a lat-long. Top right corner, up pops a lat-long. I jot those down, and that creates my bounding box. So you have to be careful, because if I create a bounding box that starts here and ends here, and it's massive, yeah, it may tell you a lot of information, but it might take hours to run. So you have to be careful that your analysis regions just start out small and then get larger with time. But you can zoom in on all kinds of things. Like, here's a nice forest reserve, right? Look how dense that forest is. If I could run an analysis from here down to here, I might see if things are happening along the edge of this dense forest, or is any of that being devegetated? So did that answer your question, the way that you choose a lat-long region?
Yeah, sure.
So just be careful. Just be careful running really large regions. Start small, get an idea for how fast it runs, and then increase your bounding box slowly to something larger if you desire.
Yeah, it's clear.
Any other question?
Sure.
Yeah. I just want to know how you determine the NDI threshold.
NDVI threshold.
NDI threshold.
NDVI?
Yeah, threshold. How do you determine that?
Someone wants to know, how did you determine the NDVI or NDVI thresholds?
The NDVI threshold. So the way I would do that is, let me see if I've got a plot of NDVI. I don't plot that one out directly. Let me see. I'm going to show you real quick while I have you on here. I'm going to pull up a plot of NDVI from another notebook here. Let me just do this. Indices, Tanzania. This is just one that I had run earlier. I want to show you if I have an NDVI plot. Here's one here. This is NDVI plot here in the middle of the screen. This is an area in Tanzania over, it looks like the following. This is just a grassland area. It's a cropland area. You see all the croplands in here? It's grasslands and croplands. So NDVI is probably the most common vegetation index. Now, it is, if you go out and you read in the literature, first thing is the index ranges from 0 to 1. That's a definite. The least it can be is 0, the most it can be is 1. And if you read in the literature, grasslands and croplands are typically 0.2 to about 0.6, and forests are typically 0.6 to 0.9. So it's just commonly known in the literature. People have studied this, and they have determined that the vegetation index gives you readings for certain kinds of vegetation in the range. So this particular area here, remember I told you was croplands. So if I just went from 0.2 to 0.6 and just plotted this one and reran it, I'd have to rerun this whole thing. It would give you that range. So I'll just rerun this one and see what it looks like. So the way I determined that for you is, the first thing I did was I said 0.6 to 0.9 was forest. So I started out with forest. And then later on, when I was looking at change, this was the change plot. It was quite arbitrary that I chose only show change between 0.2 and 0.6 is the stuff in red. That's where I got this answer here. So again, this threshold here, 0.6 to 0.2 for my loss, I just chose that, I wouldn't say randomly, just by saying I am only looking for significant changes in vegetation, and I want them to be at least a drop of 0.2 all the way down to 0.6, because if I'm starting out at 0.6 to 0.9 and I drop 0.6, I know that that's probably deforestation. There's nothing else that can be dropped that significantly. Now, it is possible with a cropland that a cropland could start out at about 0.4, 0.5 during its peak, and it could fall 0.2 during the harvested period. That's a possibility. So is it possible some of this area here is croplands that have just been harvested and therefore the vegetation has dropped? Yes, it's possible. But remember the region we're looking at. The region we're looking at is forests and urbanization. There's probably not a significant amount of croplands here. So again, when I do these things, if you go out on the web and you investigate a little bit about NDVI and just read into it, you will see that what the community accepts as regions of NDVI that represent croplands and grasslands, and regions of NDVI that don't. So again, right here, I plotted here 0.2 to 0.6 for this area in Tanzania. This one's a little darker. That's like a 0.6. So that's pretty dark. But all this area in here is 0.2 to 0.6. These are grasslands. These are probably rangelands that they're using for cattle in this area because they're in this range of 0.2 to 0.6. This is just the NDVI. And then later on, I create a threshold plot where I say, show me the NDVI that's just between 0.2 and 0.3, and this is what I get. So I guess I hope I'm answering your question here. NDVI is commonly known to represent certain kinds of vegetation with ranges, but the choice that I made for vegetation loss, but the loss of 0.2 to 0.6 in NDVI was a rather arbitrary choice, but I think it's one that reflects a major loss or a loss in trees, likely in forests, because forests will drop dramatically because they start out as dark, dense vegetation, and they almost typically go to either bare soil or grasslands, and the drop is significant.
Okay. Yeah, okay. Question? Yes. You go ahead.
I want to know if I can use NDVI to analyze the level of urbanization, or should I use the normalized difference built up area to analyze the level of urbanization? Which one of the two?
I'm not sure I understood that question again. Could you repeat a little bit slower? You're asking about NDVI.
Yes, I said if I can use NDVI because NDVI to analyze the level of urbanization, or should I use NDVI to determine the level of urbanization?
To do urbanization?
Yeah, so he's pretty much asking which of the indices is better to assess or analyze the level of urbanization, NDVI, NDBI.
Yeah, it's B. B as in boy, NDBI. Let me go up and I'll show you the ones in the urbanization. So in the urbanization notebook, there are a few indices that we plot, and here they are right here. All right, so here is NDVI. There's the definition of NDVI. There's the definition of NDBI, and you can go out and look at these on just Google. If you Googled NDBI index, you'll get some lots of papers out there about this. It's a very commonly known way to do urbanization. And then there's another one. I don't like it as well. It does okay, but it's called the buildup index, and it's a combination of NDVI and NDBI. It basically takes NDBI and subtracts NDVI. So basically it takes the buildup index and removes vegetation and gives you another thing called buildup index. I find I don't like it as well. I just like the straight NDBI, which is buildup index. And here they are. So again, if you look at the equations, it's the near infrared band minus the red over the near infrared plus the red. Data set's just the name of our data set. Then the buildup index is the SWIR band, shortwave infrared 1, minus the near infrared band over SWIR plus near. So notice NDBI only uses infrared bands. It is not using the bands in the red, green, blue, which we would see with the naked eye, red, green, blue. These are infrared bands. And what's interesting is the infrared bands tend to reflect and tend to scatter the imagery coming back from urbanized areas is impacted in these infrared bands quite well. And so what happens is if you have an area that is mostly buildings and structure and roads and bare soil, you will get bright reflectance in the SWIR and near the infrared bands. And so that's why this index is built up on that. Whereas vegetation, the red and the near infrared tend to do a good job of picking up vegetation. So again, a lot of this is out in the literature, but that's the difference between them. There are other bands out there, like if I go over to this indices, there's another one called Enhanced Vegetation Index, It's right here. It's an alternate to NDVI. And here's the equation. It's near infrared and red times 2.5. And then it takes a little bit of the blue band. So you can create your own equation, and you can put in here anything you want. Up here, where is it in the, whoop, I missed it. Sorry about that. Actually, it was in the urbanization. You can create new indices here, add them in yourself, create them here, and plot them just by modifying this notebook. And again, the way you modify this notebook, if I want to create a new one, I just do insert, cell below, and now I can define, a new one, and I can just put a new one in here. I can copy this one down, and I can create a new index. And you can do this on the fly and do anything you want, but there's a whole lot of ways to do this. So I hope that answered your question. I think you were getting at NDVI versus NDBI and what are the differences.
Okay. Hi, Brian. Thanks very much. That's a very wonderful presentation, and I think the data cube concept, it's great, and I think we're going to make use of it. I have some few questions just to understand. I think during the answer to some of the questions, I actually addressed them. One of the things you just ended up with was the possibility for us to actually create our own indices, and they use in different band ratios and band combinations. I know the examples have been more built-up areas and land cover change. I know the Landsat 8, and again, most of the examples you showed, we are using the Landsat 8 and Landsat 7.
Yes.
For those of us who belong to Generation X, we've been doing a lot of analysis using Landsat 5. Starting from 1984 upwards right to 1999 when we had Landsat 7. Is there opportunity to use Landsat 5 images within this data cube if you want to do analysis going back, temporal analysis going back 30 or 40 years? And if yes, how do you address the differences in the terms of the bands? Because considering Landsat 8 has 11 bands, Landsat 7, 8, and then Landsat 1, they'll be using different, Landsat 5 will be using different sensors. How do you reconcile those differences in sensors as well as the banding ranges? What I mean by that, say for Landsat 8, you have 2 bands in shortwave infrared, and there's only 1 in Landsat 7. Now, if you want to compare, 2 data sets or analysis that have been done years back using Landsat 7 for a particular area, and now you want to use Landsat 8, how do you reconcile those differences within this particular data cube? Then the other question was, in terms of the radiometric resolution, I know the Landsat 8 is using is 12 bits, whereas the other one is 8 bits. And of course, in terms of the data values within those pixels will be different based on the intensity you can capture. How do you address that? Is there a way this has been addressed?
Excellent questions. So let me start with a few comments here. First, we are in the process right now of gathering all of the Landsat 5 data for all of the 5 countries in the African Regional Data Cube. And we expect probably within the next, probably just next month or two, we're going to add Landsat 5 data to your cubes. So Landsat 5 data is coming, which will give you data back to 1984. So a lot more data. Here's the problem, though. Africa in general was covered fairly lightly by Landsat 5. Landsat 5 had a duty cycle that was a little less. It had a data recorder that was a little smaller. So there's not as much data, but there is, enough. There's enough back there that you'll be able to go back pretty far and run these same notebooks and start to look at things. So be curious, right, to run urbanization and just run this NDVI index on Landsat 5 back in 1984. You might see some dramatic changes, in urbanization around Freetown. Now, The other question you had, even more interesting, is how do I reconcile using these 3 different data sets, Landsat 5, 7, and 8? So yes, there are differences between them, but I will say that USGS and NASA, when we built these Landsat missions, we purposely tried our very best to maintain the time series and the consistency between these missions so that people could do long-term time series analyses and not be overly concerned with the significant difference, with the differences in the bands. Now, you're right that Landsat 8 is now 12 bits. I think it's 12 versus 8 bits. There's more content and information and more accuracy. Yes, there is some new bands in Landsat 8 that we didn't have in Landsat 7. But I would argue that the core bands, the ones that you typically use for most of your analyses, red, green, blue, near infrared, SWIR 1, those bands have remained stable and are very similar between all of the missions. And so, yeah, there's some subtle differences there, but I've seen time series analyses that have combined Landsat 5, 7, and 8, and there's not a big difference. Now, if you run an NDVI analysis with just Landsat 7 and an NDVI analysis with just Landsat 8 over the same region for the same time period, Landsat 8 data tends to give you just a slightly higher NDVI, we've noticed, just because of the bands themselves, the way they built the bands, the spectral range of the band is slightly different. So it actually accepts a bit more energy return when it looks down at the ground. And so the bandpass filter is slightly different. And so it's never going to be exactly the same. But I would say if you're looking for significant changes, if you're just looking at things like urbanization extent, I would say that you can use these 3 together quite well, and I don't think you're going to have significant issues. But that's something for you to investigate. Look at analysis with L5 only, look at an analysis with L7 only and L8 only, and start to look at the overlap time periods. So, so that's coming soon. Landsat 5 is coming soon, and you're going to be able to run all of these analyses in the same exact way.
Okay, wonderful. One final question, just highlight. I just want to know, is there an opportunity as well, apart from the Landsat series, to bring in things like the ASTA data set? The reason I'm asking this exercise has been focusing on land use change and NDVIs and others. Well, we want to see if we can use the data cube for natural resource management, especially within the mining industry for reconnaissance exploration. We have relied extensively on the shortwave bands, especially band 6 and 7 in Landsat 8, and then the band 5 in Landsat 7. Now, those, we are limited by 8 bands and 11 bands, but the ASTA has 14 bands. Is it possible to bring in the ASTA data set and combine them with the Landsat data set within the data cube?
Yes, short answer is yes. And we actually would love to have you bring in that kind of data and use it. So remember, one of the things that we're building up to is that Strathmore University and their decision to take on the management of the data for all of these cubes. This is something that I will need to work back and explore with them, because it's not a significant amount of data because it's larger scale, right? It's like 250 or 500 meter. And it could conceivably be quite easy to pull that kind of data in and to regularly have it. So I'll explore that with Strathmore, because again, they're the ones that should be building these cubes and pulling them together. This is something we could probably automate quite rapidly. So I will look into that, but that's a really good question. And it could help you out, like you say, with mining detection and other things. And it gives you more data because it's taken on a daily basis.
Thank you.
Go ahead.
I'm finished.
Any other questions?
Well,
Yeah,
Elizabeth,
go right ahead. In the meantime, I'm going to bring up another document on some other data sets, but go ahead.
Mine is not a question, but a comment. You mentioned the NDVI that you can consider regards to Waterloo area, and that you were referring to that maybe a glass field. One thing that is common in the western area here is that you have a lot of urban agriculture taking places in more especially along the edges of Britain, or where you have creeks and all the rest. So it's very possible that what you're referring to, that it might be a grass field. This can be urban agriculture areas that have been cultivated, and also depends on the time period. Maybe you also have because you also have these places are cultivated, especially those in the swampy areas, in the dries, and then when those places get water, they have to get up onto the upland. So you may have, if you take the normal traditional way of classifying images, you have a lot of mixed pixels in those regions. So that's also a possibility.
So you were breaking up a bit. I didn't understand all of that question. If someone else could repeat, was the question was about using the NDVI in some other regions to maybe investigate, was it mining or some of the other problems?
No, what I was saying that you talk about the lady asked a question regards to how do you determine the NDVI threshold?
Oh, the NDVI threshold. Yeah.
Yeah, and now you talked about the situation where you're referring to that where you have a low NDVI. These are possible. These are grass fields that may be used for ranches.
Oh, absolutely. Yeah, for rangelands. Yes.
What I'm saying is that in this part of Western area, both in the rural and urban settings, you have a lot of urban agriculture taking place in places like that you're referring to, as this would be ranch areas that will be used for raising animals. So those are places that are possible that they are urban agriculture areas, because if you use the traditional classification methods, these areas often have mixed pixels, and these are really not areas that you have animals are being raised. There are places where you have a lot of urban agriculture, and these is very serious because you have a lot of urban agriculture taking place both in the Waterloo area, especially those that are very close to built-up areas. So that's what I was comment on.
Yes, so it's interesting. We had that same question in in Tanzania. So in Tanzania, this area right here is a rangeland, an area. So this rangeland that they use for livestock and cattle and so forth. And these areas have obviously different vegetation indices than something like forests. And so what you can do is I'm getting some feedback there. If you run your analysis for these rangelands, you might change your threshold, like to go from 0.2 to 0.6 to pick up rangelands, or maybe 0.3 to 0.5 or something, if you just wanted to pick up rangelands, and then you could see if those rangelands are changing. So if you did a max, you go back to this urbanization, not the NDVI one. So if you did a max NDVI and use this NDVI anomaly, you could change the baseline. Instead of being forests, you can make your baseline range of 0.6 to 0.9. You could change it to 0.2 to 0.6 and say, I'm only interested in rangelands. And then you could look at anomalous behavior in rangelands. So you can do similar things for deforestation. You could look at rangeland change. So yes, very possible to do that. Another thing I wanted to mention to you was an analysis that we have just recently done in Kenya using radar data. Oh, I'm sorry, go ahead. You had a follow-up question?
No, I think the team in Senegal trying to ask you a question. Maybe when you're done, we ask them to.
Okay. I'll make a quick comment here on other data like radar. We have just created a data cube using annual mosaics from the ALOS mission, which is a Japanese mission, a radar L-band mission. And what we have seen is it does an amazing job of detecting deforestation and land change because L-band data can see through clouds, so there's never a cloud issue. And they have created data for these epochs, these time chunks. I think they created data for like 2007, 8, 9, 10, 15, 16, 17. So you have like 7 time slices. This is what it looks like. This is an L-band mosaic. So this is 2001 over an area. This area right here was devegetated. And you see it starts to show up in a different color later on. Here it is if I plot one of the bands of radar before and after. You see the darkness here, all devegetated here. Clear as can be, no issues with clouds. Then I run a threshold analysis that I ran here. And here's my result. This is just done with L-band radar from ALOS. And on the left-hand side, all the red pixels are pixels that have changed, that have fallen within this change threshold of 0 to 2500. All the red pixels are likely deforestation. And if you compare that on the right, this is the global forest map from Matt Hansen, which is probably the only global deforestation product you'll find out on the internet. And look at the difference between the two. They're pretty darn close. I get this little feature here is right here. The main portion that was deforested in the middle is clear. The portion here, this is non-trees, and I pick those up as non-trees, and these are deforested. I get the patch here. It's really remarkable. It does a fantastic job of detecting devegetation. But again, it's a different set of data, but the beauty of the radar data is it's cloud-free, and it's a nice way to look at land change across your area other than using Landsat. It's just an additional way, and we're going to try to get this ALOS data compiled for all of the countries because I think there's some really powerful things you can do with ALOS radar as well.
Right. Okay. Brad,
Go ahead.
My question is coming from the mineral point of view. Like for instance, I have my license area, and I want to know the effects of artisanal mining within my license area. The first question is, if I have a coordinate system that is something different from the geographic coordinate system the Landsat is generating, is it possible for me to input another coordinate system which is different from the geographic coordinate system into the system? That's the first question.
Yeah, so are you talking about selecting a region based on a different coordinate system?
Yes, sure.
So what if, so one of the things we're working on is the ability to, instead of inputting a region here, like, you know, I do a Latlon bounding box. If I gave you the ability here to input a shape file, would that work?
Yeah, I think that would be wrong.
Because at least, you know, a different coordinate system. So the cube itself, we cube the data based on a given coordinate system, and it's all in Latlon, you know, WGS84 Latlon type coordinates. But
so the cube is compatible to UTM coordinate system.
yeah, you can definitely do that. So I would probably need a bit more information about precisely what it is you're trying to do. But if it's just a matter of selecting a region based on a different coordinate system, like you use some other methodology for your coordinate system, if you had a shape file, we could input a shape file here, and then that shape file would show up on the map, you know, precisely some, you know, jagged shapefile box. So that's something we're working on right now, is adding shapefile capability. So that's coming soon.
Brian, I think I think I can resonate with what he's asking. The data cube is allowing us to put in longitude and latitude, and that's more of a geographic coordinate system. Yes. Yeah. What if you have a projected coordinate system that's more planimetry, like the UTM, which is in meters? If you put that in, considering, I mean, your map is generated using the geographic coordinate system, will that not skew the map a bit because you're not using a frame projection? And if you put in the UTM directly, which is in meters, without actually specifying the projection parameters, then you're gonna definitely have a map that's gonna be skewed, especially over a larger area. Is there an opportunity to put in, apart from longitude and latitude, to put in projected coordinate system?
Sure. Hadn't thought about that question precisely, but I like it. I definitely, because I know a lot of people deal in the UTM coordinate system in meters, and so I think that would be quite easy to do, because for your area, are you a single UTM zone? Do you know?
So no, two
of them.
Yeah, we have two zones.
Okay, so what we could do is we could build, I could build a little code that would go in here. So let's say in here, instead of putting lat lon, you entered in, you know, a UTM north, UTM east coordinate range. We would just put a little code in there to convert it so that the system understands where it is, and then when it'll draw the proper region on the map. So yeah, that's a great application, and we can do that for you. We'll get the guys to put together a little code that allows you to put in a UTM. I guess it's northing and easting position, correct?
That's correct. Yeah. I think
yeah. And then it'll convert. And you think you have two UTM zones?
Yes.
Okay. And then so the first thing it'll have to do is it'll have to figure out which zone are you in, and then it'll use the coordinate transformation in each one of those zones to transform it and put it on the map so that it actually does the proper conversion into lat lon and throws it on the map. So yeah, I think that would be easy to do, and I think that would be worth adding.
Yeah. Any other question?
I'll take an action to do that. So there's two actions I see coming out of here that I think are of high value. One is this UTM capability. Actually, three actions. The next one is Landsat 5 data. I'll keep you abreast of when that occurs and when that's pulled in, because that's very important. And then this idea of getting some other data like Aster in the system, I think that would be valuable to you as well. I would also say if you have any specific use case needs, so if you're not able to use these notebooks and you have a question and you say, you know, I have this use case and I'm not sure how to do it, or I'm not sure the best way or what kind of application or code to use, I'd be more than happy to help you out. Just let us know what the use case is and perhaps we can work on it. One of the ones we've been working on is this mining detection. It's a very difficult problem. And when I get some more information on the mining detection and have some more experience with the notebooks, I'll send you back a note on that with a little document to tell you what we found about the illegal mining, and I'll have a notebook available for that.
Right. Any other? Yeah, Brian, just shortly, you might help to ask the team in Senegal if they have any question for you. I crave your indulgence. All right.
Senegal? Are they out there? I haven't heard anything yet. Senegal,
yeah.
Or do you have any questions?
Yes, I think that we will discuss that and then figure out how best to, you know, articulate our issues into one place so that there's some sort of, you know, funnel process. And then, yeah. Hello, Jake. Yeah,
Senegal be all right. This is Sedina. I'm all right.
Okay, you're okay. Sardinia,
Yes, I'm all right.
can you send me
Yes.
an email, if you would, with your contact information? And one thing I could do for you, I will take these notebooks that I just did today for training. I will put
Yes.
those notebooks into your Senegal site, and I
Yes.
will send you the training document, and I'll put those notebooks out there for you, and I'll make sure that you have the proper web address for your user interface and your notebooks, because they're different. And I'll make sure that you get that information.
That would
Then
be great. That would be great.
You could do everything we did today on your end. Okay.
Yeah. So Sene, we're looking at the training later in the year for Senegal, and that would be aligned with Brian's availability.
All right. So I'm going to send you an email. Yes.
Yeah, but if you have a question right now, if anyone in that room has a question right now to ask Brian, just go ahead quickly.
No, I didn't have a question. It was pretty clear for me on my end.
Excellent.
Okay, great. I know Sheikh is also on the line. He was trying to talk to me now. I don't know if he's got anything, or perhaps the guys at CSC or DAPSA or ANASIN or whatever. Anyone? Okay, so I think what we'll propose is Brian has given us a calendar.
All right.
We'll plan along with that calendar. We're looking at December 6 to 7 for Sierra Leone, and December perhaps 7 to 9 for Senegal. Rose has already taken the window that is open in end of November. So we're taking the period open for 6 to 9 December for both Senegal and Tanzania, and it's easy to cross the board in West Africa. So the November ending could be for Tanzania and East Africa for the physical on-site training, and then we do 6 to 7 for Sierra Leone, and do 8 to 9 for Senegal. Yes, that's right, 6 to 7.
Excellent.
All right. Okay, we'll do a one-day training. Yeah, 6 to 7, and then we'll travel to Senegal. All right. So we will be in touch. We'll figure out how that will work out. While we also sort out the institutional issues before that training. All right.
Okay, great.
Okay, great. So in the absence of any other, I'll ask the EPA, Statistics, Sierra Leone, and Agriculture to say a word of thanks to Brian.
All right.
Thank you very much, Brian. Today we are very happy because the last time we met in Nairobi, only 3 of us. Today we have over 20 of us here. So I think the knowledge that we gain today will be replicated in all in our institutions. What we want to do, but we communicate to you later, is that we are going to put all our efforts together and then make sure that we get a platform where you will be sending me questions and then getting answers from you. So we appreciate your effort, and then we hope and pray that you continue giving us the maximum support that is required for us to develop our own data cubes and analysis and our data management. Thank you on behalf of the entire team. I want to say a very big thank you to you for your time and then also the support you've been giving us. Thank you very much.
Thank you. I will ask the lady on the team to also say a word to you. Bonnie.
Okay, thank you.
Thank you so very much. This seminar is very good for us as we are trying to get ourselves together to kickstart in Sierra Leone. Thank you so very much. We appreciate you.
Yeah, my pleasure. I'm glad we were able to do this today. I know it's a little harder to do remotely like this, but it's at least it's a start. Hopefully we can work out this face-to-face training here in the end of November, early December. That might be a great opportunity to get together face-to-face and really dive in a bit deeper. So we'll continue to work on those plans. But yeah, thanks for your time today, and it was great to see that you had a large number of people on your end and such interest in all of this, because I really think there's a lot of power and capability here, and we just need to bring you up to speed and teach you how to use it, and I think you will really find it exciting. Thank you.
Absolutely, absolutely, Brian. Come on.
Yes, Brian, and the truth is that this training is an opportunity for us to explore, bring in experts within the country, because previously we were just limited. That's Sierra Leone, EBA, and Agric, and very few other partners. But today, we have a lot of people here, a lot of enlightened people in geospatial analysis, and I'm pretty sure that from now henceforth, we are on the right footage, and then we're going to make things possible. I really appreciate this training today, and then I'm pretty sure we're going to make it forward. Thank you for your presentation, and then for bringing us together. Thank you. And
Surely.
thanks.
I also, you know, I've been recording this as well, so I will send you the link for the recording. So if anybody else wants to go back and listen to a portion of this, or use this for any other training purposes, we'll have this recorded, and I'll put it up on YouTube, and then hopefully you can have access to it.
Thank you.
Right.
Okay. All right. So with that, we'll close this out today, and I look forward to talking to you again.
Thank you, Brian.
Have a great day, everybody.
Thank you so much. Nice day.
All right. Bye now.
Bye. Yeah, thank you, everybody. Just to close this out, and then we'll take a lunch and we'll depart, is the need for us to agree, because if we leave here, trust me, we've got loose ends, and I need us to tie up the loose ends. You know, when